Welcome to this presentation on the sucker rod pump, a fundamental artificial lift mechanism in the oil and gas industry. My name is Mohammed Salah Ramadan from Cairo University's Petroleum Engineering Department. Today, December 1st, 2024, we will delve into the intricacies of this vital piece of equipment. In the realm of petroleum production engineering, the primary objective is to efficiently and economically bring hydrocarbons from the subsurface to the surface. As reservoir pressure declines over time, natural flow may become insufficient. This is where artificial lift methods become indispensable. A sucker rod pump, often referred to as a beam pump or rod pump system, is a prime example of such a mechanism. It is designed to lift crude oil and other associated fluids from the wellbore to the surface, playing a critical role in sustaining production rates and maximizing hydrocarbon recovery. Artificial lift encompasses a range of techniques and equipment employed to enhance or restore the flow of hydrocarbons when natural reservoir energy is no longer adequate. These methods are crucial for maintaining economic production from mature oil and gas wells, ensuring the continued supply of valuable resources. Let's now examine the key components that make up a sucker rod pump system, starting from the surface equipment. The first critical element is the prime mover. This is the power source for the entire pumping unit. It can be an electric motor, an internal combustion engine, or a natural gas engine. Its primary function is to rotate a shaft, initiating the mechanical process of lifting fluids. Connected to the prime mover is the gear reducer. As its name suggests, this mechanism is designed to reduce the high rotational speed of the prime mover while simultaneously increasing its torque. This conversion of speed to torque is essential for providing the necessary power to drive the heavy pumping action. The gear reducer then transfers this optimized power to the crank. The crank is a crucial link in the system. It is a rod attached to the gear reducer at one end and to the pitman at the other. The crank's role is to convert the continuous rotary motion supplied by the gear reducer into the reciprocating, back and forth motion required to operate the pump. This conversion is fundamental to the up and down movement of the sucker rods. Continuing with the surface components, we have the pitman. This rod connects the crank to the walking beam. As the crank rotates, the pitman moves up and down, effectively pushing and pulling the walking beam, thereby transferring the reciprocating motion. The equalizer bearing is a critical connection point. It connects the walking beam to the pitman and helps to balance the weight and force exerted by both the beam and the pitman. This balancing act is crucial for smooth and efficient operation of the pumping unit, reducing stress on the system. The walking beam is the prominent, long metal bar that characterizes the visual appearance of a sucker rod pump. It moves up and down in conjunction with the polished rod. The walking beam is supported by a center or saddle bearing and pivots on a Samson post, a vertical structure that provides stability and holds the beam in place. The walking beam's motion is directly responsible for the up and down stroke of the sucker rods in the well. Finally, the horse head is a distinctive component, named for its unique shape. It acts as a counterweight, balancing the weight of the walking beam and the entire string of sucker rods in the well. The horse head is attached to the polished rod by a cable or chain, and its counterbalancing action helps to reduce the power required from the prime mover, improving overall energy efficiency of the system. Moving further down the system, we encounter the bridle. The bridle is typically connected to the polished rod and follows the curve of the horse head as it moves up and down. Its design ensures that the pull on the sucker rod string remains vertical or nearly vertical throughout the stroke. This vertical alignment is crucial for maintaining a good liquid seal at the surface and for efficient transmission of force to the downhole pump, minimizing wear and tear on the system. The polished rod is a smooth, precisely machined metal rod that extends from the bridle into the wellhead. It passes through a critical sealing device called the stuffing box. The polished rod serves as the direct connection between the surface pumping unit and the downhole sucker rod string, transmitting the reciprocating motion from the surface to the pump below. Finally, the stuffing box is mounted on top of the wellhead and plays a vital role in preventing leaks. It creates a seal around the polished rod, effectively containing the produced liquids and gases within the wellbore and preventing them from escaping to the surface. This is a critical safety and environmental component, ensuring that the well operates without uncontrolled fluid release. Now, let's move to the downhole components, which are crucial for the actual lifting of fluids. The sucker rods are a series of steel rods, typically 25 to 30 feet long, threaded at both ends to allow them to be joined together. These rods form a continuous string that connects the polished rod at the surface to the downhole pump. They are responsible for transmitting the reciprocating motion from the surface pumping unit to the plunger in the pump. The pump barrel is the cylindrical housing of the downhole pump. It provides a sealed chamber within which the plunger reciprocates. The integrity of the pump barrel is essential for creating the necessary pressure differentials to draw in and expel fluids. The plunger is a piston-like component that moves up and down within the pump barrel. Its alternating motion creates suction on the downstroke, drawing fluid into the barrel, and pressure on the upstroke, expelling fluid upwards. The efficient operation of the plunger is central to the positive displacement mechanism of the sucker rod pump. Two critical valves control the fluid flow within the pump: the standing valve and the traveling valve. The standing valve is located at the bottom of the pump barrel. It opens during the downstroke, allowing fluid from the wellbore to enter the barrel, and closes during the upstroke to prevent fluid from flowing back into the well. This ensures that the fluid drawn into the barrel is retained. Conversely, the traveling valve is positioned above the plunger within the pump barrel. It opens during the upstroke, allowing the fluid above the plunger to be lifted towards the surface, and closes during the downstroke to prevent backflow. The coordinated action of these two valves is fundamental to the continuous and efficient lifting of fluids. Like any artificial lift system, sucker rod pumps have their own set of advantages and disadvantages, which influence their applicability in various oil and gas production scenarios. Advantages: efficiency. Sucker rod pumps are highly efficient in lifting heavy loads over significant depths, making them a suitable choice for the majority of onshore oil wells. Their mechanical advantage allows for effective fluid extraction even from deep reservoirs. Versatility. These pumps can handle a wide range of fluid properties and volumes, from light crude oils to heavy, viscous crudes, and even fluids with some gas or solids content. SRPs demonstrate considerable adaptability, making them a robust solution for diverse well conditions. Durability. Compared to many other artificial lift methods, sucker rod pumps have a relatively simple design with fewer moving parts. This inherent simplicity contributes to their durability, reducing the likelihood of mechanical failure and extending their operational lifespan. Cost-effectiveness. The straightforward design of SRPs translates into ease of installation and maintenance. This, in turn, results in lower operating costs over the life of the well, making them an economically attractive option for long-term production. Disadvantages. Rod failure. One of the most common operational issues encountered with sucker rod pumps is rod parting or failure. This can occur due to fatigue from continuous cyclic loading or corrosion, especially in wells producing corrosive fluids. Regular inspection and material selection are crucial to mitigate this. Inefficient operation. The presence of gas or solids in the produced fluid can significantly impact the efficiency of sucker rod pumps. Gas interference can lead to gas locking, where the pump loses its ability to lift fluid, while excessive solids can cause wear and tear, leading to reduced performance and increased maintenance. Limited application. While highly effective onshore, the application of sucker rod pumps is somewhat limited in offshore environments. Their large surface footprint and the dynamic nature of offshore platforms often make other artificial lift methods, such as electrical submersible pumps, ESPs, more practical for offshore operations. However, there are still some niche offshore applications where SRPs are utilized. Let's now delve into the operational mechanism of the sucker rod pump, which is based on the principle of positive displacement. The downhole equipment, primarily the pump itself, orchestrates the fluid lifting process through a series of coordinated actions. At the heart of the downhole pump are the pump barrel and plunger. The pump barrel, a stationary cylinder, is securely attached to the production tubing. Within this barrel, the plunger, which is connected to the sucker rods, reciprocates up and down. This creates a sealed chamber where fluid is drawn in and expelled. Controlling the fluid flow are two critical valves: the standing valve and the traveling valve. The standing valve is positioned at the bottom of the pump barrel and functions as a suction valve. The traveling valve is located within the plunger itself. The pumping action unfolds in two main strokes: the upstroke and the downstroke. During the upstroke, as the plunger moves upwards, it creates a vacuum or low-pressure area within the pump barrel below the plunger. This pressure differential causes the standing valve to open, allowing formation fluid from the wellbore to enter and fill the pump barrel. Simultaneously, the traveling valve, being above the plunger, remains closed, lifting the fluid already above it towards the surface. Conversely, during the downstroke, the plunger moves downwards. As it descends, the pressure inside the pump barrel below the plunger increases, causing the standing valve to close, preventing fluid from flowing back into the wellbore. The increased pressure also forces the traveling valve to open, allowing the fluid that was previously below the plunger to move above it. This action displaces the fluid upwards, pushing it closer to the surface. This continuous, reciprocating motion, transmitted by the sucker rods from the surface pumping unit to the downhole pump, ensures a steady and efficient lift of hydrocarbons from the reservoir to the surface. The coordinated opening and closing of the standing and traveling valves, driven by the plunger's movement, are fundamental to the effective operation of the sucker rod pump in extracting valuable resources. In conclusion, the sucker rod pump remains a cornerstone of artificial lift technology in the oil and gas industry. Its relatively simple design, robustness, and cost-effectiveness make it a preferred choice for many onshore production scenarios. Understanding its components, from the surface pumping unit to the downhole pump and its intricate valve system, is crucial for optimizing production and ensuring the longevity of oil and gas wells. Production engineers play a vital role in monitoring, optimizing, and continuously improving the performance of these systems. By carefully analyzing well conditions, fluid properties, and pump performance, they can maximize hydrocarbon recovery and ensure the safe and efficient operation of sucker rod pump installations. Thank you for your attention. We hope this voiceover has provided a comprehensive understanding of the sucker rod pump and its significance in petroleum production engineering.